Hi everyone, and welcome to part 3 of our unit on hydrogeology. Our learning objectives for this part are to calculate the hydraulic gradient and groundwater flow rates, and to identify groundwater flow directions using hydraulic gradients and/or potentiometric surfaces. To get started, picture a hill slope where the ground surface elevation is shown by the elevation head, HE. Imagine precipitation falling on a hill slope and forming overland flow here at point A. We know that it would flow down the slope, right? In this direction. But what happens to the rain that falls here at point B? Does it flow to the right or to the left? To determine this, we need to look at the slope or hydraulic gradient of the land surface. This is calculated as the difference in elevation between 2 points divided by the horizontal distance between them. Between points A and B, the hydraulic gradient is 15 meters minus 13 meters divided by 5 meters, or 0.4 meter per meter. Between point B and C, it is 1 meter per meter. So how does this help us determine flow direction? We assume that the water will follow the path of steepest descent. That is, it will go in the direction of the highest hydraulic gradient, flowing from point B to point C. This example was set up for flow on a hillside, but groundwater flow is the same. We just need to remember to add in the pressure head and determine hydraulic gradients based on total hydraulic head, which is elevation head plus pressure head, not elevation head alone. Similar to the contour lines of constant elevation shown on a USGS topographic map, a groundwater map shows contour lines of equal groundwater potential, or equipotential. These are indications of the total potential energy in the groundwater system, measured as total hydraulic head. So if the map to the left shows the lines of constant hydraulic head in plan view, the cross-sectional view looks something like this. If we were to install piezometers at the location of the contour line shown to the left, the elevation of the water in the piezometer would be equal to the corresponding equipotential line. We can use both lines of equipotential and piezometer measurements to determine groundwater flow direction, which is indicated by flow lines. So if we're trying to draw the direction of groundwater flow, we know that it will always go from high hydraulic head to lower hydraulic head. So from line A to line B. But how will it get there? Will it follow this yellow line? No, it will not. We know from our previous example that flow will follow the path of steepest descent. The steepest hydraulic gradient means that the distance, L, between two measurement locations must be a minimum. The shortest distance between line A and line B will be perpendicular to them both. Therefore, the groundwater flow lines will always cross lines of equipotential at right angles. We can use this knowledge to identify groundwater flow directions whenever we receive information on groundwater equipotential, whether it is in cross-section or plan view. For example, this illustration shows lines of equipotential as dashed red lines. The water table is indicated by the transition from the yellow vadose zone to the green saturated layer. Overall, we can see that the red numbers increase from the left to the right. This is because the elevation of the water table is increasing as we go uphill. Total hydraulic head is higher here, where the groundwater is being recharged from infiltration, and head is lower at the stream. Water flows from high head to low head. Since the surface water level is flat over streams and lakes, the line of constant head are therefore pulled parallel to the surface, where they're vertical during the horizontal flow sections. We can also determine groundwater flow directions in plan view. Once again, the groundwater flow lines are perpendicular to the lines of equipotential. Notice the way that potential lines bend near the stream. They form a V that's pointing upstream. This is an indication that this is a gaining stream and that groundwater is flowing into the stream. The curved equipotential lines cause the flow lines to curve towards the stream. In a gaining stream, equipotential lines point upstream, just like elevation contours. Now that we understand hydraulic gradients and the direction of groundwater flow, we can discuss how to calculate groundwater flow rate. Henry Darcy was a French engineer who worked for the Paris Sewer District. He was experimenting with sand columns to use as filters to improve water quality and performed experiments to determine how fast water could flow through the sand column. Through these experiments, he determined that the flow rate was proportional to the hydraulic gradient across the column, and this relationship has become known as Darcy's law. According to Darcy's law, the groundwater flow rate is equal to the hydraulic conductivity times the cross-sectional area perpendicular to the direction of flow times the hydraulic gradient. The units of Q are volume per time, such as cubic meters of water per day. The hydraulic conductivity is the same physical property that we have discussed previously when discussing soil infiltration and drain flow. As this table shows, when discussing groundwater movement, hydraulic conductivity can vary just as widely as it does in a soil, with flow rates through a sandstone aquifer being 1,000 times greater than flow rates through an unfractured granite bedrock. The cross-sectional area of flow will depend on the particular situation being calculated. When describing lateral flow to a stream, the cross-sectional area is determined by the length of the stream reach, or width of the aquifer, shown here by B, times the total saturated thickness, H. When describing vertical recharge to an underlying aquifer through a restrictive layer, the area in question is the plan area of the recharge zone being considered, shown here, and those dimensions are B times X. Because the cross-sectional area is often difficult to pinpoint in real-world situations, groundwater flow rate is often presented as the specific discharge, or groundwater flow normalized by the cross-sectional area. Specific discharge is often referred to as the Darcy velocity, since it has units of velocity, length per time, but does not represent the true velocity of water movement through the pore spaces of an aquifer. The difference is that Darcy's law, and therefore specific discharge, assumes that groundwater is traveling across a cross-sectional area A. But we know that in reality, this cross-sectional area is filled with the rock and gravel particles of the aquifer, so that water is actually only traveling through the pore spaces. When we adjust the cross-sectional area to account for the porosity, we get an expression for the average linear velocity. This reflects the true velocity of groundwater movement, suitable for calculation of contaminant transport. Let's do an example of groundwater flow. A confined aquifer has a source of recharge to the right here, where it is open to the surface. Hydraulic conductivity, K, for the aquifer is 50 meters per day. The piezometric head in two wells, 1,000 meters apart, is 55 meters and 50 meters respectively, above a common datum. The average thickness of the aquifer is 30 meters, and the average width of the aquifer is 5 kilometers, or 5,000 meters. What is the rate of flow through the aquifer? So we know the equation for groundwater flow, Darcy's law, and we know that cross-sectional area for lateral flow is the aquifer width, B, times the saturated thickness, H. The given quantities are listed here. Now for our solution. Cross-sectional area is the 30-meter thickness times the 5,000 meter width. Hydraulic gradient is the difference in hydraulic head divided by the distance between the two wells. Note that the direction of the difference isn't that important. If you calculate a negative gradient, it indicates that the flow direction is from the second piezometer to the first, not from the first to the second. The flow rate is then found to be 37,500 cubic meters per day. For the same aquifer system, we now know that the porosity is 0.2. What is the average time of travel from the head of the aquifer to a point 4 kilometers downslope? For this calculation of travel time, we need to know the linear velocity. We know that the Darcy velocity, little q, is groundwater flow divided by area, and the linear velocity is the Darcy velocity divided by the porosity. We also have our values of groundwater flow and area calculated previously, and we were given that porosity is equal to 0.2. So using the groundwater flow rate in the area from the first part of the example, the Darcy velocity is 0.25 meters per day. Once divided by porosity, this yields the true linear velocity of 1.25 meters per day. This example shows that water moves very slowly underground. At a rate of 1.25 meters per day, it will take almost 9 years for groundwater flow to make it from the recharge zone to a discharge zone 4 kilometers away. This concludes part 3 of Unit 8. You can explore groundwater flow directions further using the groundwater flow Quizlet.